Welcome back. In the last class, I started discussing about carbon 13 NMR, where I introduced some salient features of carbon 13 spin, where we discuss, as I have been telling all along, the gyromagnetic ratio of carbon is 4 times less. As a consequence, the energy separation is less, sensitivity is less. In addition to that, carbon 13 has abundance of only 1%. Taking all those factors into account, we discussed and I showed that carbon 13 is nearly 5,700 times less sensitive compared to that of protons. That's one point. Secondly, I also said when the carbon 13 is only 1% abundant in a molecule containing one carbon, possibility of seeing carbon 13 in that state is only 1%. That is, if there are 100 molecules, there may be only one molecule which has carbon 13. So the probability of seeing that is 1 in 100. And I said if there are two carbons, it is going to be 1 in 10,000. And I extended the logic and I said if there are, let us say, 6 carbons in the molecule, this is not uncommon in most of the organic compounds, you will see there are large number of carbons present. I just took a simple example just to point out a molecule has 6 carbons. What is the probability of finding all the carbons in carbon 13 state? This is 1 in 100, 1 in 100, 1 in 100. Each of them is 1 in 100. The probability, the joint probability of seeing them is a product of all these things. That is, it turns out to be 1 in 10 to the power of 12. It is 1 in a quadrillion. Just look at this number. Such a very, very small number. It means probability of seeing all the carbons in the carbon 13 state at a time is practically 0. You will not be able to see all the carbons as carbon 13. Then the question can be asked, if that is the case, how can we see all the carbons in a molecule containing large number of carbons? This is a valid question which we need to answer. How can we get all the carbon peaks in spite of the fact the probability of seeing all of them in the carbon 13 state at a time is practically 0. So before going to that, let me introduce, of course we'll come to that point, so we'll answer that in 1 or 2 slides. Before that, let me point out how does protons attached to carbon 13 influence the spectrum. This we should know so that we can go and answer many questions. How does protons attached to carbon 13 influence the spectrum? Remember, there may be a CH3 group in the molecule. There may be a CH2 in the molecule. There is a CH and also a quaternary. All different types of carbons we can think of. Only these 4 types of carbons which you can normally think of in any given molecule. If there is CH3 carbon present in your molecule, the carbon 13 signal will be a quartet. Why it is a quartet? Because carbon 13, probability of seeing all the carbon in carbon 13 state is practically 0, I pointed out. So each carbon now will not be seeing the other carbon, okay, for interaction. They will be seeing only the protons which are attached to that or the protons attached to the next carbon. First, let us see this carbon. It is seeing protons attached to that. That means there are 3 equivalent protons, chemically equivalent. Then what is going to happen? Just apply 2Ni plus 1 rule. There are 3 chemically equivalent spin-off nuclei coupled to carbon. What you will see? It has to be a quartet of intensity 1, 3, 3, 1. Clear, right? Now, What about CH2 carbon? Exactly I say these two protons are equivalent. Again apply 2n plus 1 rule. This carbon will be a triplet. And what of the carbon attached to a single proton? This we have come across many examples like CHCl3. And what we are going to see is this is coupled to only single proton which is bonded to it. As a consequent, this is going to be a doublet. The quaternary carbon, which is not attached to any of the protons directly, there is no directly bonded proton, it will be a singlet. Okay, this is the general pattern you expect for any carbon in the carbon spectrum. Of course, you ask me a question, what happened to the long range coupling which we saw in protons? Of course, it will be there. We will come to that later. But by and large, if generally there are two types of spectra recorded in carbon 13. One is fully coupled, fully decoupled. Of course, sometimes we used to do off resonance decoupling, where you ensure only the carbons which are coupled to directly bonded protons, that coupling pattern is seen. For example, the experiment is done in such a way, this carbon will only couple to these three protons, and we are going to see only coupling of CH3, the carbon CH3 protons. So it will be a quadrat. Similarly, it will be a triplet. Then it will be a doublet and no coupling at all. This is a type of spectrum normally it used to be seen. And if you want to do a fully coupled spectrum, there is definitely a possibility. This carbon not only can see the protons coupled to it, you can also see the protons which are 2 bonds away or 3 bonds away. This is also possible. But at the moment, we'll concentrate on this. When the directly bonded protons are there, CH3 groups is a quartet, CH2 is a triplet, and CH carbon is a doublet, and a quaternary carbon or any carbon which is, or a CO carbon like that, which are not attached to any protons, will always be a singlet. This is a point which we must remember. Now take a simple hypothetical example of the molecule. Let us say I have a molecule like this. It is a hypothetical molecule. Don't go by practicality of these things. That type of molecule exists or not, I don't know. I'm just for discussion purpose I'm taking. If I have a hypothetical molecule like this, in the carbon 13 spectrum, I get a quartet for this, I get a triplet for this, I get a doublet for this, I get a singlet for this. Of course, depending upon the substitution here, we get particular pattern. You understand, the carbon 13 spectrum cannot have any other pattern apart from this. Only I am considering directly bonded proton coupling. That's all. These are the only 4 patterns you can think of. Now, look at the spectrum of this molecule. We have a molecule like this, a realistic spectrum. We have a CH2 and a CH3. What were we seeing in the proton spectrum? These 3 protons coupled to these 2 protons, and this made it a quadrat. These 2 made these 3 protons as a triplet. There was a coupling between the 2 protons through chemical bond. Now we are not worried like that. When I am looking for this carbon is coupled to these 3 protons only. As a consequence, you see, it is a quartet. This carbon sees these 2 protons, so it is going to be a triplet. Now look at the other carbons here. Each of these carbons, you see, you can see this is a doublet because there is only 1 proton attached to it. It is a doublet, this is a doublet, and this carbon is not coupled to anything, and it is a singlet. It is a very nice example to see in a realistic spectrum. We can see all possible carbons present, all types of carbons, like CH3, CH2, you have different types of CHS, aromatic CHS, and also you have a quaternary carbon unattached to proton. You also have a CO carbon, etc. So all of them are seen here. This is the pattern normally expected. Okay. Now let us look at the carbon 13 spectrum of ethanol. It is all well known, CH3, CH2, OH. What did I say? We always see this carbon coupled to this proton, this carbon coupled to this proton. So you must get a triplet and a quartet. Quartet for this carbon and a triplet for this carbon. That's fine. Before that, this pattern I wanted to, please keep this in mind. The type of pattern we are going to get for different carbons. Now, let us try to understand again the probability of occurrence of each carbon in carbon 13 state and carbon 12 state. This we discussed, and we said in a large molecule of containing 6 carbons, probability of seeing all the carbons in carbon 13 state at a time is 1 in a quadrillion. That's what we said. Now let us go slowly. I'll ask few questions for which we have to get the answer, and then with our carbon 13 spectrum becomes more clear for us. Now in the ethyl alcohol, what are the possible isotopomers we can think of? The possible isotopomers we can think of are, this carbon can be carbon 12, this carbon can be carbon 12. I said this probability is 97.8%. It is NMR inactive. This can be carbon 13, this can be carbon 12. It is only 1.1% NMR active. This I said and I am repeating again to make you understand. There is another isotopomer. This is carbon 12. This is carbon 13. This is only 1.1% NMR active. And the probability of finding both the carbons simultaneously in carbon 13 state in this ethyl alcohol is 0.000121%. This also I showed. This is NMR active, and only this isotopomer is totally NMR inactive. Okay, the signal from this isotopomer is very difficult to see. We already saw. Probability of seeing this is so difficult. You will not see carbon 13 both simultaneously present. This isotopomer peak is not seen. It's very difficult to detect. Now let us get the spectrum of carbon 13. Now I consider this isotopomer. What is the type of spectrum I am going to get? That's why I introduce carbon spectrum when it is coupled to 3 protons. When CH3 is there, I get a quadrat for this isotopomer. Perfect. This is what we understood. When carbon is coupled to 3 protons, we get a quadrat. Now what about this isotopomer? It gives a triplet. Right? But in reality, in the given sample, take your sample in the NMR tube and take the spectrum. You have 1% of the molecule in this state, 1% of the molecule in this state. For example, you take, let's say, 100 molecule. 1 in 100 molecule will be this, and 1 in 100 molecules will be this. That is the probability. Since there are 2 different types of carbon, you have to take 1 in 10,000 will be this, and 1 in 10,000 will be this. Okay? No, I'm sorry, 1 in 10. 10,000 is for 2 carbon percent. Okay. So now, when I see this carbon, this separation gives me 1 bond J carbon proton coupling between carbon and 3 protons. Understand? This separation gives me coupling between carbon and proton. Fine. What about this triplet? This separation gives me 1 bond coupling between carbon and this proton. Now, in a realistic situation, when I take the NMR spectrum, all these isotopomers are individually present, right? And NMR spectrometer will not distinguish what is what. It simply gives you the spectrum of every isotopomer at a time. Now, the total spectrum is a superposition of these two. You understand? So, if you real carbon 13 spectrum, if you take of ethanol, you get a spectrum from this isotopomer and you get a spectrum from this isotopomer. And together, this is a realistic spectrum what you saw. And this is what you are going to see. Now the question is, what about the carbon 13 coupling? Probability of finding both of them is 1.5, 1 in 10,000. You can ignore it. This if a natural abundant carbon 13 couplings are not seen also. But remember, molecule having carbon 13 both simultaneously C13 In principle, we may get the carbon-13 spectrum of that, but probability of finding is so low, you can ignore. So basically what you are going to see is the spectrum for each isotope individually, which are superimposed. Okay, and carbon-13 couplings in natural abundance is not detected, because again they say low probability, but does not mean coupling is zero. That you don't say it is non-existent. It exists. Only thing is we don't see it. That's all. I hope the point is clear now. Okay. Now we'll ask you another question. What about long-range proton-proton couplings which are affecting the carbon? But remember, when I was looking for this ethyl alcohol spectrum, I saw these two protons coupled to this one makes it a triplet. These three protons coupled to this proton makes it a quartet. That was there in the proton spectrum. And just because you are now looking at the carbon-13 NMR does not mean this coupling do not exist. That exists, right? That coupling also exists. Now what about those long-range proton-proton coupling? What happened to that? How do they get reflected in the spectrum? Let us look at it. Now, if I look for this carbon-13 isotope, we got carbon-13 proton couplings here, which was a quartet. But at the same time, these two protons also coupled to this. And as a consequence, carbon-13 spectrum is going to be a triplet because of CH3 carbon. CH3 carbons will be a triplet because of CH2 protons. You get the point. This is quartet because of these three protons, and it is a triplet because of this coupling. This carbon is also coupled to this and also coupled to these two protons. Remember, these two protons, don't think when these protons couple to this, you cannot say this is not coupled to this. This is a long range coupling. So this carbon is not only a quartet because of this, it is also coupled to this one and forms an additional triplet because they are equivalent to protons. Remember, I am looking for carbon now. Then you may ask me a question, what happened to proton-proton coupling? Again, don't get confused. The passive spins. So proton-proton couplings you are not going to see here. You see only coupling between the active spin and passive spin. You get coupling of this carbon to these three protons, which is a quartet. Coupling of this carbon with these two protons will be additional triplet. Okay. So that will be coming into the picture. I'm sorry, this is a mistake which is made. It is not 3JHH, it is 3JCH. Okay, we'll come to that. So similarly, this is also 3JCH. It is not HH. I said HH will not be seen. I said that. So this is HH. Okay, we'll see this. And this is what it is. It is 3 bonds CH coupling is also seen. And similarly, here also, if I look for this CH2 carbon, you are going to get coupling of this carbon to these two protons will be a triplet. And in addition to that, these three protons also coupled to this carbon. Is it clear now? So carbon can experience simultaneously coupling to other protons also. Okay. Earlier I said we were seeing only quartet, but I'm now bringing in the long range. See, not this is long range CH couplings. Okay, long range CH couplings are also getting reflected here. Fine. Now CH2 protons will be a quartet because of this coupling, and CH2 carbons will be a triplet because of this, and also because of CH3 protons it is going to be additional quartet. Let us look at the spectrum now very carefully. What is 1JCH? This is the spectrum. This is CH3 and this is CH2. You understand? We are seeing these things. Now, this is a Now, one bond coupling. Okay. Now, this is a realistic spectrum where CH3 carbon coupled to 3 protons and is a quadrat. CH2 carbon is coupled to 2 protons and is a triplet. Now, there is a long range 3J-CH coupling. The protons also couple to this carbon. What is that long range? For these two protons, there is also these three protons. These three protons coupled to this carbon. What will happen now? Each lane of the triplet is going to become a quartet. Is it clear now? Each lane of this triplet is going to become a quartet. Similarly, here also, directly bonded carbon to 3 protons will be a quartet. It is only a stick plot I am giving you to make you understand. Directly bonded carbon to protons will give rise to a quartet. But there is also remotely bonded proton to this carbon. What will happen? Then each carbon line, which is a quartet, is going to be a triplet. So what is happening is, we are looking for long-range CH couplings are also possible. If I look at a molecule like this, we have a directly bonded carbon-proton coupling, which makes this a quartet, and it is also having a long-range protons coupling to this carbon, which makes each lane of this quartet into a triplet because of this. Exactly same here. It will be triplet of a quartet. It will be quartet of triplets. That is the real spectrum you see. If a carbon-13 spectrum is real spectrum is obtained, bringing all protons coupled to all the carbons, is a fully coupled carbon-13 spectrum. Assuming these long-range couplings are seen, now this carbon, if you see, CH3 carbon is going to be quartet of triplets. Hope you are all clear what I am telling. So large coupling, the quartet is because of direct CH coupling, and triplet is because of long range carbon proton coupling. Similarly, it is going to be triplet of protons. This is exactly what we are going to see in the realistic spectrum. If you see all protons coupled to all the carbons, this is what it is. Look at this CH3 proton, CH3 carbon. This CH3 carbon is a quartet because of for one bond CH coupling. This is a big quartet. And these two protons also coupled to this carbon, long range proton carbon coupling. Then what is happening? Each lane of this quartet is a triplet. This CH2, if you look at it, this carbon proton coupling is a triplet. And this carbon is coupled to these three protons. As a consequence, each lane of this triplet is a quartet. You understand? Similar to proton spectrum, but here we are observing carbon-13. We are seeing carbon proton coupling one bond and carbon proton two bonds coupling, or 2 or 3 bond coupling we are seeing. Okay, this is what we are seeing, and that's what, if you can see the spectrum of other carbons also, we can interpret like that. So what do you understand from this? For a molecule containing n chemically non-equivalent protons and chemically non-equivalent carbons, the detected proton spectrum is from a single molecule, because all the protons are 100% abundant, and simultaneously you can see all the protons present in the molecule. You can get the spectrum directly. All the peaks from all the protons can be obtained from a single molecule, no doubt at all. What about carbon-13? Carbon-13 spectrum is a superposition of spectra from n isotopomers. It is superposition of spectra from n isotopomers, each containing one carbon in different positions. If there are 10 carbons in the molecule, in the real carbon-13 spectrum, what you see, it is not one spectrum. It is 10 spectra, each corresponding to different carbons. They get superimposed, and that is what you are seeing in the carbon-13 spectrum. You understand? Please remember, you are not seeing a spectrum from a single molecule in carbon-13. Every carbon in this carbon-13 position will be an isotopomer. 10 carbons have 10 isotopomers, and then individual spectrum of each of them are seen. Like I gave the example of ethyl alcohol, all of them will be superimposed. As a consequence, carbon-13 spectrum is not from a single molecule or single isotoper. It is always what you see is a superposition of spectrum of different isotopers corresponding to the number of equivalent carbons. So simple formula, remember, if there are n chemically inequivalent carbons in your molecule, there are 10 NMR spectrum corresponding to each carbon in carbon-13 state. That they're all superimposed, and that is what you are seeing. Please remember this. Now we'll come to strength of CH coupling. What is the approximate value of the carbon couplings, everything, which you should have an idea. Like proton-proton couplings, I said, 1-bond coupling, 2-bond couplings, 3-bond couplings, etc. In the case of CH coupling, 1-bond carbon-proton coupling, if it is sp3 hybridized carbon, it is around 115 to 125 Hertz. If it is sp2, it is still larger. sp carbon is 240 to 270 Hertz. 1-bond coupling, remember, 1-bond 1JCH. So as the hybridization stage, depending upon the type of hybridization, if it go to sp hybridized carbon, the carbon proton 1-bond coupling is 240 to 270 Hertz, quite large. For sp3 it is much less, and sp is the largest, and sp2 is in between. This is the important you should know when you are analyzing the carbon-13 spectrum. Similar to proton spectrum I showed you, for different functional groups of the carbon also, there are varieties of groups for which the chemical shift ranges have been more or less identified. Supposing if I have a carbonyl carbon, I have to see the peak somewhere around 160 to 220 ppm. I told you carbon-13 goes from 0 to 300 ppm, unlike proton. If I have to see aromatic carbon, I'll see the spectrum from somewhere around 100 to 140, 150, like that. If I have a CH3 carbon, it is somewhere around 20 ppm. Exactly the chemical shift pattern what we saw in the proton, similar trend is there here also. There, whatever the factors which affect the chemical shift of protons will also affect the chemical shift of carbon in the same manner. There is no difference. Okay, so that's why you can look at this chart, and then from the chart you can identify which carbon is coming where, and the interpretation becomes much easier. Similarly, if you look at the electronegativity and carbon-13 chemical shifts, exactly what we saw in the case of protons. Now take an example of a molecule CH4 where one proton is knocked off and fluorine is substituted. This comes at 71.6 ppm. Instead of fluorine, if I put chlorine, you get 25.6. Instead of chlorine, if I put bromine, it comes to 9.6 ppm. What does it tell you? Again, more than electronegativity, it withdraws electrons from the carbon. As a result, that carbon shifts downfield. That's exactly what we observed in proton, right? The logic is same. The phenomena is not different. So depending upon the substituent of the negative atom, electronegativity of the substituent, the chemical shift of the carbon start changing like this. So bromine is least electronegative compared to carbon, much less compared to chlorine. It is 9.6. Chlorine is less electronegative compared to fluorine, comes at 25.6, and the fluorine is the most highly electronegative atom. When it is attached to this, it comes at 71.6. Now you can see that here also. As we saw, CHCl3, CH2Cl2, CH3Cl, CCl4, we observed in the proton. Of course, we don't see CCl4, but now let us see what happens as we see the number of chlorines which are bonded to carbon keeps increasing in a molecule like this. If if one of the proton is replaced by a chlorine, it comes at 25.6 ppm. If the two chlorines are bonded to same carbon, see it comes to 54. When three are there, it is 77.2, and all the four protons are replaced by chlorine, it comes to 96.1. This is exactly what we saw in proton. Depending upon the number of electronegative atoms which are attached to particular carbon, more the electronegativity atom substituted, what will happen? It will get more de-shielded and starts moving to the low field. So that means higher ppm value it goes. Exactly the trend we are observing. Clear? So we have different groups like this. If I have a carbonyl carbon, these are all given in the chart which I showed you earlier. Are many, you can see this type of information is available in the literature quite a bit. If I look for the carbon like this, which are attached to two oxygens like this, the chemical shift ppm approximately around 90 to 100. For like carbon, which is two carbons like that, which is bonded to commonly bonded to a oxygen atom, it is 50 to 75 ppm. Similarly, this carbon attached to OH group is around this range. So like this, we have a varieties of things. Electronegativity of effects in the carbon can also be seen. For example, especially for the CH3 group, I took an example. If I have a CH4, it take the molecule. In the case of proton, we saw this highly shielded 0.23 ppm. Now carbon also goes to CH4 is highly shielded. It goes beyond TMS, minus 2 ppm. Similarly, in the one of the proton is replaced by NH2, then it comes to 2.5 in the case of proton, the CH3 proton, whereas carbon 13 it goes to 27 ppm. Similarly, if I go to CH3OH, so instead of this proton attached to carbon comes at 3.4 ppm, where carbon comes at 50 ppm. This carbon, which is highlighted, all colored in red. Now CH3F, these three protons in the proton number comes to 4.3, whereas carbon 13 it comes to 75. Exactly, the trend is same. See there, if proton is coming to the downfield, the carbon attached to the same proton also follow the similar trend. That's what I wanted to show you. The electronegativity effects on the particular CH3 group, how it affects the proton spectrum. In the like manner, the carbon 13 is all chemical shields are also affected. But only thing is the range is here 0 to 10. Here is range is from 0 to 300. Corresponding to the chemical shield values are quite large here. That's the only difference. Okay. Okay. We see that now again we saw what happened as the chain length increases. We saw the induction effect when they substitute the electronegativity atom, how it affects. We saw that in proton also. Now a long chain molecule is taken. Hypothetical molecule. Don't worry what is attached or anything. What is this molecule? Now one of the proton is replaced by a chlorine here. Now this carbon comes at 45, this carbon comes at 33, 29, 22 and 14. Only I am concentrating the carbon here. The carbon chemical, you see what happened? The one which is directly attached to electronegative atom, that carbon is lowest, comes almost downfield at highest ppm value, that is 45 ppm. As you keep on going, this the next neighbor like that, the induction effect keeps reducing, and if you come to the CH3 carbon passive, practically its effect is quite a bit reduced and it still comes at high field. So this is what I wanted to show the electronegativity effects also has the same inductive effect what is like in proton, but the trend also similar, it keeps reducing as the chain length increases. The de-shielding effect of chlorine is very clearly seen with the increasing of the number of bonds. What about the hybridization effect? Same. Look at the hybridized carbon here. These different types of carbons. sp3 carbon is more de-shielded than sp2. That is a simple formula. You remember, it is a general trend. sp3 hybridized carbon, if it is there, that is more shielded than sp2 carbon. Now similarly, sp carbon is more shielded than sp2, but less shielded than sp3. Order you remember now. Which is more shielded? sp3, then sp2, then sp. The shielding effect and the chemical shift, if you want to say, first is more shielded is sp3, then sp2 and sp. So sp3 carbon comes at high field, then sp2 carbon, then sp carbon. That is the way the trend follows. So sp3 carbon is more hybridized than sp2, and sp hybridized is more shielded than sp2, but less shielded than sp3. This is the trend. So carbonyl carbons are more shielded, we can see here generally. And if in a molecule like this, we have all different types of carbon is there. Aromatic carbon comes around 120 to 140 ppm. Carbonyl comes at 170, and CH3CH2 will come similarly. CH3 generally comes between 10 to 20 ppm. This is 20 to 30 or 40 ppm, like that. So these are all similar trends, similar to proton chemical shields. Okay, look at the different types of carbons when it is attached with what is the R group, the type of R what you are going to have. As a consequence, the chemical shift varies like this. So these are all general ideas, general information. I take a carbon like this, type of carbon, RCH2Br. Bromine, chlorine, this is what we saw for a CH3 group. Similarly, if you have an R attachment like this, how this carbon chemical shift is affected? Same trend follows the similar trend you can see. If I have a RCH2Br and if R group is this one, then chemical shift of particular carbon, this carbon, is around 110 to 125 ppm. Extend the logic like this. If you have a RCH2OH, if R group is, let us say one of them, I didn't write. Okay, R group is, let us say for this, is C double bond O, and R is on either side, this and this. This carbon comes at very downfield, 190 to 220 ppm. So this is the type of information we get especially for the different chemical shifts of carbon. So in a realistic example, we get a spectrum like this. It's big molecule. This is a carbon-13 spectrum. Now your job is to analyze. First you have to simplify the spectrum to identify the number of carbons. Remember, it is a carbon spectrum. You have to assign peaks to each carbon. How you do that? This is a procedure by itself. You understand? This is the, now we have to start analyzing the carbon-13 spectrum. So today I will stop here. Today I gave you an idea about how carbon-13 spectrum is affected when there is a directly bonded protons are there, how the carbon is split because of the remotely bonded protons, and what are the types of factors that influences the chemical shift, range of chemical shifts of the carbon, and I also pointed out the factors that affect the chemical shift of protons also affect similarly the chemical shift of carbon, etc. So I'll stop here. In the next class, we'll start analyzing the such a spectrum of carbon-13.